In this video, we continue our discussion of echelon form and reduced echelon form with a discussion of pivot positions and the row reduction algorithm. So this video is really about how to take a matrix and row reduce it into its echelon form or n echelon form or its reduced row echelon form. So here are a couple of facts. If you're using row operations to produce an echelon form of a matrix, or when we use operations to produce an echelon form of a matrix, the further operations that are used to go from an echelon form to a reduced row echelon form do not change the positions of the leading entries. In order to tell you or to explain why that's true or why that's intuitively true to me, I want to look at an echelon form of a matrix. Remember, when it's in echelon form, it already has that stair-step pattern. We have leading entries. Here is a 1, there's a 2, there's the -5. And you see them as you're going from left to right, just sort of stair-stepping down in that echelon form. That's what that echelon means. And we have zeros below those. If we're trying to get from this to reduced row echelon form, that means I want all the leading entries to be 1. So I might take this second row and multiply by 1/2 to make that a 1. Or I might take the third row and multiply by -1/5 to make that a 1. But when I multiply these by constants in order to rescale that row so that my leading entry is 1, I'm not changing the positions of the leading entries. I'm just changing that 2 into a 1, and I'm changing that -5 into a 1. Now, if I'm trying to get into reduced row echelon form, I not only want this to be a 1 and this to be a 1, I want all of the entries above that to be zeros as well. We already had all the entries below that as zeros when we were in echelon form. In echelon form, these are zeros already. So in addition to that, we want these to be 1s, and we want the values or the entries above those 1s, those leading 1s, to be zeros. So I would want this to be a 0, and I would want this to be a 0, and this to be a 0. Well, making this a 0 requires multiplying this row, or actually taking this row and adding it to a multiple of this row. Because if I take a multiple of this row and I add it to this row, I can use this to make that a 0. And I can do the same thing if I take a multiple of this row and add it to this row, I can use that and make that -9 a 0. So as we're doing that, as we're going from echelon form to reduced row echelon form, all of the operations that we engage in don't change the values or don't change the positions of those leading entries. That this leading entry is going to be right here in that first row and first column. And this leading entry is going to be in the second row and the second column. And this leading entry is going to be in the third row and the fourth column, even as we continue through to try to make all of these leading entries into 1s and to make the values above the 1s into zeros so that we're in reduced row echelon form. So that's a fact. Those entries, those leading entries don't change position as we're going from echelon form to reduced row echelon form. And since the reduced row echelon form of a matrix is unique, the leading entries are always in the same positions of any echelon form obtained from a given matrix. Now, this is not this is not unique. This is the result of a number of row operations. This is the echelon form of this matrix, or an echelon form of this matrix. But I could have used a different different sequence of row operations to get to a different echelon form. But regardless, since the reduced row echelon form of a matrix is unique, even if these 3 numbers are different in different echelon forms, their positions are going to be the same in all of the echelon forms. Because when I take those and rescale them and then multiply by constants to get these entries to be 0 above this -5 and this entry to be 0 above the 2, when we're doing all of that, even if we're starting with different numbers here in the one in this position, and this position, they're all going to be starting at the same location because they're all going to the same place. And they're going to that same place of that reduced row echelon form that is unique for that matrix. So these positions, the positions of the leading entries in the echelon form of a matrix, are so important that we give them a name. We call those pivot positions. That is a pivot position is a location in a matrix that corresponds to a leading one in the reduced row echelon form for that matrix. A pivot column is just a column that contains a pivot position. And a pivot is a non-zero number in a pivot position that's used to create zeros in other rows above it via row operations. So I have a matrix here, and I'm not going to show you how to row reduce this matrix into this matrix, although I could. We're going to do a different example though. But you can row reduce this matrix into this matrix. This is an echelon form of that matrix. Now, when we are trying to identify the pivot columns, these are columns containing a pivot position, and a pivot position is a location in a matrix that corresponds to a leading one in the reduced row echelon form of that matrix. The pivot position in this case, pivot positions in this case, are this position, and this position. It's the positions of the leading entries. Now, I don't want you to be distracted by the fact that there are numbers in those boxes. It's really about the location. The pivot positions are here, here, and here for this matrix. And you might say, how are those pivot positions? Because that's where the ones go in the reduced row echelon. That's where the ones will go in the reduced row echelon form for this matrix. So it's really about the location and not about the entry in that location. So these boxes represent pivot positions of this matrix. I'll call it A. So this is the pivot. These are pivot positions of A. Now, pivot columns are columns that contain pivot positions. So this is a pivot column, this is a pivot column, and this is a pivot column. And I'm not pointing at those numbers at the bottom. I'm talking about the entire column. So that column, and that column. Or over here in the echelon form or in an echelon form, that column, and that column are the pivot columns of this matrix. And again, I'm referring to the entire column, not just the zeros at the bottom here. Now, a pivot is a non-zero number in a pivot position that's used to create zeros in other rows in that column via row operations. So the pivots it's definitely not that zero. Aren't these numbers over here? It's not the 0, the -2, and the 3, which happen to be in the pivot positions of this matrix. The pivots are 1, 2, and -5. 1, 2, and -5 can be used to make that 4 into a 0 and that -6 and that -9 into a 0. So those are pivots. And then we would call this first one a pivot as well, even though we're not going to use it to make zeros above it. We could use that one to make zeros below it. And we would tend to do that as we're going through the algorithm to create the echelon matrix, or the echelon matrix in the first place. So let's list those pivots in this example, in this particular echelon matrix for this, this specific matrix A, are 1, 2, and -5. They're just the leading entries when we are in echelon form, or in an echelon form for the matrix. Okay, so now that we have this terminology under our belts, we can talk about the row reduction algorithm that will allow us to take a matrix and convert it to an echelon form, and then take that matrix in echelon form and convert it to its reduced row echelon form. I'm going to list the steps on the right-hand side as we go through this row reduction algorithm. I think it's It's clearer and easier to see what's going on when you see an example. So we will use the right-hand side as our outline of the algorithm. And the left-hand side is where we will provide a concrete example of this. And again, the row reduction algorithm is just a procedure for transforming a matrix into echelon form or reduced row echelon form. First, you want to begin with the leftmost non-zero column. The leftmost non-zero column will be a pivot column. The pivot position will be at the top of that column. Now, the first step in the algorithm is identifying that leftmost non-zero column, recognizing it as a pivot column. And then we want to select a non-zero entry in that pivot column to be used as our pivot. That might require interchanging rows. Okay, so let's look at our example. So let's say we start here. We've got a matrix with 3 rows and 4 columns. The leftmost non-zero column is this one. And so we're identifying that. This is a pivot column. And the top spot in that pivot column is a pivot position. And then typically we want to select a non-zero entry in the pivot column to be used as a pivot. But we've already had a 1 there, so I think that's going to be a good choice. Okay, the next thing we do is we use row operations to create zeros below the pivot. Now, when I took linear algebra, it was clear to me that I could get to reduced row echelon form in many ways. I wondered to myself, like, why do I have to follow this algorithm? Can't I just take any path I want to get to the answer, to get to that version of the matrix that has that stair-step pattern with zeros above and below our leading ones? Like, why do I have to do it this way? You can do it lots of different ways, but this is the most efficient way. the reason we have this algorithm is because it makes our life easier. So if you want to take a different path, you can. You're just going to be doing a lot more operations than are necessary. This is nice because it's going to get you to that reduced row echelon form, if that's what you're seeking, in the most efficient way possible. So now we're going to, let's follow this step. We want to use row operations to create zeros below the pivot. I'm going to call this row 1. I'll call this row 2 and this row 3. Now I want to get rid of that 4 in row 2. So what I will do is I will take row 1 and I'll multiply it by -3, or excuse me, -4. And then I'll add it to row 2. That's one of our elementary row operations. That's legal. So let's do that. Now, if you want, you can work this out on paper. Like you can do -4 times this row and then list row 2 and then add them together. I'm not going to do that. I'm just going to do the arithmetic in my head. I'm going to leave row 1 alone. So -4 times this row and added to this row. -4 times 1 is -4. -4 plus 4 is 0. -4 times 2 is -8. -8 plus 5 is -3. -4 times 3 is -12. -12 plus 6 is -6. -4 times 4 is -16. -16 plus 7 is -9. So that's my new row 2. And then we could list row 3 here and then do this again. But rather than writing the next matrix up and then doing another row operation, I think I'm going to do 2 row operations at once. So I went from here to here, and now I want to take row 3 and replace it with, I want a 0 right here. So I'm going to use this 1, that's my pivot, to make that into a 0. In order to make this a 0, I need that to be a -6. So I'll multiply row 1 by -6 and then add it to row 3. I have -1, or 1 times -6 is -6. -6 plus 6 is 0. -6 times 2 is -12. -12 plus 7 is -5. -6 times 3 is -18. -18 plus 8 is -10. Excuse me. -6 times 4 is -24. -24 plus 9 is -15. Okay. So after you've done that, you've created zeros below this guy, below this, that pivot. What you do is you just ignore that top row, and you look at the matrix that's left and you start over again. So you're just going to repeat this process. So we're ignoring the top row and then we're looking at the matrix that's left. And then we just do the exact same process again. You're going to repeat steps 1 through 3 to the submatrix that remains. Until there are no more non-zero rows to modify. So we begin with the leftmost non-zero column. That's this one this time if I'm ignoring that top row. This is a pivot column. Pivot position is at the top. So it's right here. We want to select a non-zero entry in the pivot column to be used as our pivot. That may require interchanging rows. We'll just leave this one. And then we'll use row operations to create zeros below the pivot. So this will be my pivot. But first, I would like that to be a 1 because we know that that makes our life easier. So I think I will take row 2 and replace it with a negative 1/3 of row 2. And I noticed something similar here. So I'm going to replace that with negative 1/5 of row 3. That step isn't necessary. It's actually an extra step, but it's just going to make everything a little clearer. When I take this and I multiply by negative 1/3, I get 1, 2, 3. When I take this and I multiply it by negative 1/5, I also get 1, 2, 3. I like writing it in that way because now it's clear that this row and this row are multiples of each other. So I can take row 3 and I can replace it with negative row 2 plus row 3, and this will become a row of zeros. Or in other words, if I take this row and I subtract this row, I'm just going to get 0, 0, 0, 0, 0, 0, 0. So I'm not following the algorithm exactly because I added this extra step, but that extra step made it easier for me to get to this 0, 0, 0 spot. It made it, I mean, it looked pretty obvious here, but it's even more obvious here when the rows that look identical to each other. Okay, and I believe we are now in echelon form. We've got that stair-step pattern. Looks like this. We have a leading entry here, a leading entry here. We've got zeros below that leading entry, so that's good. These first 4 steps are called the forward phase. Of the row reduction algorithm. These allow us to row reduce to row echelon form. Now, if you want to go further, if you want to get to reduced row echelon form, you've got to add an extra step. So we're going to begin with the rightmost pivot now. This is different. We went from left to right. Now we're going to go from right to left. So we're going to begin with the rightmost pivot and work upward and to the left. Creating zeros above each pivot. Pivot. And if a pivot is not 1, you want to make it 1. Yeah, you just want to multiply by a scalar. Okay, so we're here and we're almost in reduced row echelon form. The only problem is, well, we've got 1s in the leading positions. That's great. We've got a row of zeros at the bottom. This is the only non-zero entry here, but we've got a 2 right here. We need to get rid of that 2. So we start with the rightmost pivot, which happens to be right here. In order to get rid of that 2, we need to take row 1 and replace it by something. In order to get rid of the 2, I need to add negative 2 to it. So I will multiply row 2 by negative 2 and then add it to row 1. When I do that, I'm not going to change this because this is already a 0. So the one, that pivot position stays the same, just like we were talking about at the very beginning when we talked about pivot positions. If you're going from the echelon form to the reduced row echelon form through row operations like we are right here, this pivot is going to stay exactly the same because of the zeros below it. So we're leaving row 2 alone. We're leaving row 3 alone. Excuse me. But we're taking row 1 and adding -2 times row 2. -2 times 0 is 0. Or 0 plus 1 is, of course, 1. 1 times -2 is -2. -2 plus 2 is 0. 2 times -2 is -4. -4 plus 3 is -1. And then we have 3 times -2 is -6. -6 plus 4 is -2. And that's our new row 1. And now it's in row, this matrix is in row echelon form, or reduced row echelon form. We have that stair-step pattern. We've got zeros below our pivots. Our pivots happen to be 1, and above each pivot, we have 0. Those are the only non-zero entries. The ones are the only non-zero entries in those columns, in our pivot columns. And all of these are row equivalent to each other, so we're going to use these little tildes to indicate that they're row equivalent. And that's it, we're done. This is the, we can call it U if we want to. U is the reduced row echelon form of the original matrix. That we started with, which was this one. Now this part of the process where we're going backwards, we start on the right and then go backwards and go to the left to try to get zeros above those, and then to make all of our pivot positions, or make all of our pivots equal to 1 if they weren't already equal to 1. This is called the backward phase of the row reduction algorithm. It takes us from row echelon form, excuse me, to reduced row echelon form. All right, I believe that's the end of this video. Oh, one other thing I wanted to mention, there's something called partial pivoting. It's just a strategy used by computer programs. It selects the entry in the column with the largest absolute value to be the pivot. And the reason it does that is to reduce rounding error. Because when you're doing this, most of the time you're not doing these row operations by hand. Most of the time a computer is doing this for you. We want to ensure that the results that we get through these row operations, when we take a matrix and then we write it in its reduced row echelon form, we want that to be as accurate as possible. And as soon as you start talking about fractions, as soon as you have an entry that's, say, 1/3, 0.33333333, you know, for example, we've got all those threes. It can only save so many threes. The computer is only going to save a certain number of digits. And that's going to introduce some rounding error into your results. And you might not want that. So to reduce that as much as possible, um, the many computer programs use this idea of partial pivoting. Now, when I was doing this, I didn't follow that rule at all. I could have used the 6 as my pivot, but I was like, why would I use the 6 when I have a 1? The arithmetic is going to be much easier if I just take that and I multiply by -6 and I add them together. And this is a pretty nice matrix where everything worked out fine and we ended up with integers in our reduced row echelon form. So we don't really have to worry about that in these textbook problems. But when we're actually using linear algebra in the real world, we do absolutely have to worry about that. One of the nice things about the lay linear algebra book is it makes these asides about the numerical algorithms pretty often. Um, and that's important and valuable to us because not all linear algebra problems are made for textbooks and made for college classes. Many linear algebra problems um, are problems that are being solved in the real world. And so we have to understand um, how to write the programs that will reduce our error as much as possible. And this is one strategy that we can use to do that. Now, this video was about the row reduction algorithm and pivot positions and how to take a matrix and use use elementary row operations to get it into echelon form or reduced row echelon form in the most efficient way possible. And the most efficient way possible is to follow this list of 5 steps. And you just sort of start on the left and you work your way over to the right. And then that last step, you sort of go backwards and get the zeros in that top triangle. But we did not talk at all about how this relates to systems of equations. That's what we're going to talk about in the next video. So I'll see you next time to talk about how reduced row echelon form and echelon form will allow us to solve systems of equations.